Thank you. Thank you, folks. So yeah, for this theme I'm going to talk about today is it will be the very first time I'll be talking about it, and it's kind of a consequence of my last year's talks. Last year I talked about lots of ways of using shaders and combining shaders with other stuff to create unique effects. And for this, shaders is kind of like a bonus. It's the main thing here is isolates. Even FFI is a bonus here, and you'll learn about it later. I forgot to add self-presentation slide, but yeah, that's me, Renan Araujo. I'm Brazilian. I live in Portugal. Last time I was here at Flutter London was 2019, pre-pandemics, and was my very first talk in Europe. So that's why Flutter London is so special for me. Um, and yeah, it was being lots of fun since then. Uh, and yeah, so this comes from a challenge that was presented to me to create some kind of a unique UI. So uh, I know that some of you folks cannot stand talks about AI, but this will be the only thing I'm talking about AI. So this is about representing an AI agent, or it's an AI user interface, right? So this AI agent something something has some states, it's ready, can be listening or even emitting sound. So you have to represent the sound waves there. There's a processing state that's kind of a wavy thing. It should be animated here. It's not. Annoying. And a long processing, which is pretty much a sphere. And all of this using particles. So some people came to me, presented this design, and said, is this possible to do with Flutter? Um, and came to my mind several different ways you can do this kind of stuff. Particles it's a problem that was solved across the board in different technologies. Um, so doing it on Flutter would be like a first, and I tried to do this by rendering the particles in the Flutter level without using platform views or things like that. So the requirement is we should be able to interpolate, so the particles should move in between these states, especially between the tree first and the sphere, and should feel alive, should be something that feels organic, because this is the kind of experience that we expect to have when dealing with things that's based on AI, because we sell it as some kind of magic to users, so you have to represent as magic, you have to feel like magic or something alive there that's talking to you. So these were the requirements. I kind of changed the design a little bit from the requirements from the clients. It will not be too much the same, but yeah, that's it. So how can we solve this kind of problem? So if you look into that design and you don't consider Flutter, consider the whole spectrum of technologies that we have out there to solve this. So the first way you may think is a GPU-based simulation, in which we would use the GPU buffer to in parallel calculate the positions of each particle in the screen. And the GPU is ideal for that because it does things in parallel. So GPU is better at that. It's made for that. So we would have even millions of particles could be rendered even on a mobile device without having too much hiccup in performance, even 60 frames per second. So other platforms can do that. On iOS, if you use SwiftUI, metal shaders are very powerful, and I've seen people doing crazy things with that. There's also things based on web GPU, where we have compute shaders. React Native has that with Down, and React Native is Kia. But for Flutter, there is no proper way to use compute shaders or things like that natively and in a stable way. But someone yesterday, one day before my talk, decided to change the whole game, and they showcased Flutter GPU running. This is on the master channel, and it's true 3D. Spoiler alert! There are some of the folks in the Flutter in the Flame engine are working every day on porting this to Flame, so we can have 3D games on Flutter as well, and it's completely rendered by Flutter by Impeller. No platform views, no FFI to render and then pass to a platform view. This is Flutter, only Flutter. I've seen everything is written in Dart. It's pretty fun and have all of kind of shaders, vertex, fragments, and also compute shaders there. I still have to go deep on it, but probably I'll have to do another version of this talk using Flutter GPU. But this is not production ready yet. It's still very experimental. We reached all of the platforms, but it's still very experimental. As an alternative to that, we can have a CPU-based simulation. So there's lots of problems we can have with them. Memory, battery usage will be great, will be humongous depending on what you do, and you'll always be limited to a certain number of particles. From what I could do here, I squeezed every bit of performance optimization we can have with Dart, and I can reach 20,000 particles as opposed to possibly a million we could have with a GPU. But it's still something, right? So this is a pragmatic approach, how we can do that today to ship production apps using having a proper particle system. So we have several ingredients to this mix. The first one, well, one of the states of that I showed in the beginning has sound. So this pretty much steps into the territory of the last talk where we have FFI doing FFI stuff to show a UI with waveform and stuff like that. It's pretty much we need to do the same thing here. So we have several packages to do that. I'm using Flutter So Loud that has this kind of snippet, so you can have the numbers that represent the frame of sound at a certain moment. And this is So Loud is a very interesting FFI package. I really, really recommend you to try and test it out. And it's very useful for games as well because you can, it's an actual audio engine that you can mix sounds and everything's real time. It's pretty fun. So yeah, this is a way to load an MP3 and you can have a proper way of displaying a waveform there. You just have to hook into the whatever UI you're having. In this case, a particle system-based UI. All right, so this is where things get funny. So you're not gonna draw particles with several draw circles in the canvas. You have these two kind of unknown APIs from the canvas. Just so I know my audience, did any of you use one of these two? Draw vertices? Coolio. Draw vertices or draw world points? Both, nice. You as well? Yeah, so we have only two, and I think this is a bigger sample that we have than we have with the general Flutter community. I think that's less than 1%, to be honest. It's crazy how people don't know this, but this is very useful to draw things in the canvas at scale. Both of them receive kind of lists, and then they draw stuff, right? Draw vertices is useful for, I use this for mesh gradients, so you can draw, you can tessellate every bit of a patch that we have here in between control points. So we have a big mesh of triangles here to render a mesh gradient. But today for particle systems, we have raw points. So it looks like this. You have a list, a float, 32. So a list, basically a list of doubles. And then you can use that and the paint to draw on a canvas, right? So that's a very rough approximation on how to use this. And this will result in several points in the screen. But the important part here is the list. And this list is a list of coordinates within the viewport of that canvas. So it's kind of an offset from 0, 0 on that canvas. And depending on how many particles you have, let's say you have 3,000 particles, we will have 6,000 values in this list. So it grows as much as particles you have. So this is pretty much how this particle system has to look like. We have the inputs. Here we have two examples of could be the viewport size and a delta time to show move the particles around within time and have animations. But you can also have other stuff. For example, in the state that we display a waveform, there's the numbers that would represent the different values in the waveform, and other stuff, other inputs that we can have. The particle engine will take care of using these inputs and spit the list that we need to draw raw points. And then drawer points will do its job to put this on the canvas. But producing this list is the problem. The most savvy of you already realize that when you have a big list and you keep allocating it, you have a problem of performance, and also iterating on it can also take time. So let's do the very first particle system in a very stupid way. In this case, in every frame, we are allocating a new list, and we are iterating on that list and producing the proper coordinates for each particle, and then painting it in the canvas, right? This is a problem because let's imagine this ruler we have here is the frames that we have produced by the device. So while this iteration is happening, the allocation and the iteration on that list is happening, we are blocking the whole event loop on the Dart side, on the Dart isolate. And this is where everything on your app is running, at least on the Dart side. So your app will probably freeze after some frames, because every frame will trigger a new calculation, and we have junk, basically. So your 60 frames per second app probably going to be measured on seconds per frame or something like that, which is not funny. So let's be a little bit less stupid. So the problems we have, allocating is a problem. Producing that float32 list takes time with the iteration. And if that is bigger than a frame, which is around 10 milliseconds, then 10 milliseconds of very modern devices, then we have an app that feels junky, touch will feel slow, your whole app will feel slow, and probably will cause the user's device to take off and consume the battery like a game. So if you have an app and the user sees that your app is consuming like a game, then you have a problem as well, consuming battery. So let's make this mix less stupid. It's still stupid, but less stupid. So an isolate, we can understand this concept on Dart that's called isolate, and your Flutter apps running on an isolate is the main one, but you can create secondary ones. And each isolate behaves like a thread, but it's not quite a thread because each one has its memory, memory heap, memory space. So as a consequence of that, you cannot share instances of objects. So in this first trial, to make things more optimal, we can delegate the calculation of the particles positions to the isolate, and then later to the worker isolate, I'm sorry, and then the main isolate can keep rendering the UI thread, the UI without any junk. So this is how roughly, I try to be very representative here. Probably there are some bugs on this, but this is roughly how an isolate would look like. It has a receive port, and then we receive the inputs. In this case, is the count, the amount of particles we have, the size of the viewport and the delta time could be more. Uh, Produce the float 32 list and then send back to the main isolate. And the main isolate would look like this. Per frame, it would send and request the isolate for more, for an update in the states of um, the particles, and there will be a result, and the main isolate would then draw the result, which is the float 32 list. All right, so it looked like this. It's going to look like this. So we have a main isolate, and we will send the inputs. The list can be allocated only once while the worker isolate is alive, and then we can keep updating on new frames. So we don't have a location on every frame anymore, but there's a problem. We have to communicate back the, the coordinates of the particles on every update. And that's not very optimal because, as I said, isolates don't share memory. So because they don't share memory, they cannot share instances, and because of that, whenever we have an update in the state of the particles, we have to copy all of the values. And that's not optimal. It's like just like allocating on every frame again. And even the amount of objects that will be circulating in the send part and receive part would also drain the battery a lot. The memory consumption is ridiculous. So, I mean, we don't have junk, but we have at a price, right? So we have to copy the list values on every update. Why? Well, because there's no memory sharing. And there is no way to have memory shared between isolates until FFI. So let's talk about FFI. Or we should not, because we just had a talk about it, and let's not go deep on it again, right? So I'm going to change this to ingredient 4, using FFI to bamboozle Dart into having a shared memory across isolates. All right, so this is all of the FFI we're going to see in this talk. Basically, we tell FFI to allocate some memory, and when you do that with FFI, that memory is outside of the Dart heap. So I didn't test with thousands of isolates, but I'm pretty sure that almost all of Dart isolates that you spawn will be able to access that memory. So you only need to have that list allocated once, and you have the memory address, so you can send the isolate upon creation, the address of that list, and then the isolate will be able to write in the address. So we allocate only once in the main isolate, and the worker isolate will only need to write on it. So in the end, we have this shared memory outside of the Dart heap. All right, so that's why this is fast. The Dart garbage collector don't even care about this list. You'll have to deallocate the memory yourself later, otherwise you'll have a memory leak. And yes, you can even stress this out and have multiple cores of multiple kernels of that particle system working at the same time. So you can have one isolate working half of the particles and another isolate working another half. That's a little bit of stretch. I didn't do that because that would be too reckless. But in theory, you could do that. So it looks more like this. So the particle engine don't even need to return the values anymore. They just need to update the values in the list, and the main thread will be able to keep rendering the particles, even if one cycle takes longer than a frame, which on my experience takes a lot of particles to that happen. If that happens, the main thread will only find the last update of the particles in the list. So we will only have junk in the particle system, in the particle widget, not in the rest of the app. So we don't have junk. It's pretty fast because it's allocating only once. We are not copying values anywhere, and we're just reusing the same address. So we can go to the next ingredient, which is shaders. Fragment shaders is a nice way to apply some effects to it. So if you will look soon when I show the thing running, we have some kind of a glow happening in the whole particle thing, and that's a post process. So after all of it's rendered in the canvas, before Flutter sends the result of that canvas to rasterize in the Flutter engine, we can pass all of that resulting bitmap into a fragment shader, which happens in the GPU, and you can apply custom effects to it. So I'm using this for kind of a glow effect, a bloom effect. And yeah, so this is how would you do it roughly. Everything that we did would be inside of this rasterized particle to image thing, and then you can draw that in a rectangle with the shader set. There is a talk that I did about this topic on post-processing. It's on the FlutterCon Berlin channel. If you are interested about that, I covered Flame, but the talk also covers post-process on Flutter widgets, so that can be interesting as well. We apply like several different layers of fragment shaders to have just one effect, as you can see in the image. But yeah, just a call out. So let's see how this works. I'll show first the thing running that should be running but closed for some reason. Holy guacamole, where is it? Example. Oh, it's here. It's here. Let me remove the performance overlay. So this is the three first states. So processing, it's your particle running there. Looks pretty bad here on the projection, but it's running 60 frames per second on my computer if you want to look later. And also this, I just added
you didn't miss it.
I just added a audio file here, so it can represent this audio with a waveform. The audio is pretty annoying, but I'm gonna leave here. It's a WWDC from last year.
I mean, look at it. The front screen is ridiculously
So we have a particle something, particle UI representing audio, and then we have the big sphere. So this is, I forgot the name of the guy that created this concept, but there's a proper way to distribute this particles in a 3D space, but in the end, the particle system will render each one of these particles in a 2D coordinates. That's what Flutter is expecting. So you can have even advanced stuff like a camera kind of view. So here we have a distance of the camera to the, let me try to drag to the center of the particle system. We have 16,000 particles running there, and it's still pretty fast, 60 frames per second for me. I also tested this on lower end Android devices. Something around 10,000 particles is still fine for even the 99 euro Android device. You can have things like particle size, so each particle can have its own size. And in the camera also you have field of view, so you can have like a zoom or more like a fish eye kind of lens. And even max z distance is the longest distance that I allow particles to render. Particles that are too far away, we just don't render in this case. So you have that threshold here. So in this case, we can this renders only the front part of the sphere, and this also renders the back part of the sphere. That's pretty much it, and also can rotate around, calculate the speeds of the spin. Yeah. And also we can apply even shader-like, GLSL-like functions, like this applies a noise to the position of the particles, yada, yada, yada. And we can stress this out and stress this concept out and even have like something like a word map represented. I was going to build today, but all right. Yes, it's off edges, but we have a transition between one state and the other, from the waveform to the sphere. So yeah, that's pretty much it. We have some limitations. Uh, First of all, I didn't know it was possible to allocate memory on the web, so I didn't do a web version of this. But after the previous talk, where I saw a WASM malloc there, maybe this is possible on the web as well, without killing the browser or killing your tab. I mean, I'm gonna try. It's also very complex to maintain. So if you're going to recreate something like this and fork, I'm gonna publish this. It's already public on my GitHub, and I'm gonna publish some more information about this on my Twitter. So if you wanna look around, look here, um, and probably on LinkedIn as well. So if you wanna delve into this, you're gonna find a very fun code base. I didn't use much of AI to write this, and this means that the code is rubbish. Probably Claude would write something better than this. But yeah, I'm refining it. There's some rough edges, but the point is that it's possible to have a particle system today in production. Probably it will be better with Flutter GPU, but it's here already. So yeah, that's it. Questions? One question?
What algorithm did you use to drive the particle systems into shape?
Yeah, I forgot the name. It was on the top of my mind when I wrote this 4 months ago. Uh, it's somewhere in the code base. It's Euclidean sphere, something like that. Yeah, it's an algorithm that's sorry. Yes, it's an open source algorithm. Yeah, and there are lots of algorithms out there. There's one for a heart shape, which is pretty fun if you want to do something like lovely. Yeah.
Are those written in C++ or C that you need to use?
No, this is all Dart. 100% Dart. The only Dart FFI I did was a Bamboozle. It was not FFI at all. Just allocating memory, because with Dart FFI, we had lots of APIs for us to control memory outside of the Dart hip. And this is the interesting part. I want that API. Oh, it's useful for reaching codes that was written in other languages. Fine, but for this, we only need the allocation and the allocation and then the allocation, removing that allocation. Yeah.
So with the second isolate, do you know if that will run on another core? So because you've got the shared memory segments, in theory, it can store that in the caches, and you can have two cores both accessing the same memory.
Yeah. So with that comes different problems. It's solvable, but it's very complicated to solve. But the problems are, what if it takes longer for one isolate to render one part of your form and the other is shorter for some reason? If there's like a displacement even of a millisecond there, we could have very weird forms like the sphere here, for example, have half of it in one position and half of it in the other. There are ways to sync it, and I started making it, but it was so much code that I delegated to Claude, and all my tokens were gone. So, and I have Ultra. I have Anthropic Ultra, and it was all gone. It's theoretically possible, but let's not do it. I mean, maybe for something else rather than particles, there are different applications that we can have for this.
Oh yeah, no, I was just even thinking just of the setup we've got here at the moment, that it's running the main isolate on a different core to the worker isolate.
Yeah.
I mean, I don't know, maybe it's an operating system thing as to whether or not that happens, I don't know.
Yeah, for only two isolates, so we don't have ever any problems with asynchronicity. I had to fix some race conditions that, for example, if you start a frame before you finish the other, the isolate can be in a weird position. So there are some locks, some booleans that I'm transitioning between the main and the worker isolate, and that fixes everything. Yeah.
I'm just curious if you looked into whether there's like atomics or anything like that in FFI. I just haven't looked into it yet.
No, we are. What's atomics on FFI again? I'm sorry.
Like you're doing this stuff in C. Atomics are something that when you write to it, it guarantees that you write the whole thing from one thread. The whole other thread can read the whole thing from the other thread, so you don't have something happening halfway. But that's just like
Oh.
Boolean. It's like technically a Boolean should be okay, but even if you're writing to one Boolean from one thread, reading it from another, it could be a weird state. So I'm just curious if you looked into that at all.
No, I didn't look into that. I shouldn't need it, but I mean, if I will need it, it would be probably very necessary.
That would be how you write a mutex for this.
Yeah, makes sense.
With FFI,
It's like
you
going
could
back to the
with FFI, you might be able to lock that shared memory segment in your practice.
Yeah, potentially.
Oh. But would that be something like platform specific? I'll have to do one per platform. It smells like
Yeah.
fun.
There's libraries that handle that. So you might have to import a C library that doesn't.
Nice. How to render an AI thing? Yeah, I mean, I think it's worth it. I'm gonna try it.
Is there a way you could have sent like the delta instead of copying like the whole thing, or there's no way?
Sorry, it
Like
should.
when you copy the int list float entity, like every single time, is there like a way to just send the delta and update the original one?
Yeah, so it happens, the communication between isolates, it resembles a lot method channels on plugins. So you can pass, what you can pass through that tunnel is very specific types. And by default, they're always copied. So you have a float of ints. So we pass, when you pass that float of ints through the send part and receive part, the receiving part, we also receive a list and we receive all of the integers on that. But what happens behind the scenes is the receiving part created a new list, and as it's receiving integers, it's writing on that new list. So effectively, we have a new allocation. There is no way to go around that unless we use this crazy Dart FFI thing. So what's now with this implementation? What's being transmitted between isolates is a memory address, which is literally one integer, in the beginning of the isolate, and then never again. And on every frame, we are sending what I call here uniforms, which is basically inputs to a shader. It's similar to fragment shaders. So we're passing uniforms to this kind of shader thing that we have here. I can show a little bit of the code. If you have, faint hearts, close your eyes because this is crazy. So basically, this is similar to a fragment shader, but for a sphere, for a particle. So render sphere, for example, is the one in this state. So there's all of this data that I'm passing. I told you it's just a size and delta time. No, it's a lot of things. There's also weird states here that I didn't finish. Waves, like it kind of warps around the surface of the thing. This is all translated to these parameters here. And then I apply lots of math here. I don't even remember what this is doing, but it's doing all of that sphere stuff there. And yeah, all of the coordinates, apply rotation, yada, yada. In the end, we have a position. That's basically, this is a vector 2 that then I will transmit and write into the existing float 32 list that's outside of the heap. That's it.
Any more questions?
Potentially a silly one, but could you not push the entire math layer to FFI, and would that not be a bit quicker, or was this to show using Dart as much as possible?
Sorry, I'm a little bit deaf.
Can you push all of the math onto the
FFI layer?
onto the FFI layer, do all the maths on there, and then just return the result to Dart?
and the FFI layer would be written in a different language, right? Yeah, with that comes another responsibility that we have. That native code that we wrote in C, Rust, whatever, will be compiled into something. It's an artifact, if you want or not. And I didn't delve too much into that, but it's another responsibility that you have. You probably would use build hooks for that, and then after that, you have that artifact that will be called. Could be faster, yes. So this basically it would have the same thing here, but the isolate would still be here, but instead here we would have a proper call to an FFI. Yeah, it's just another way of solving it. I don't know. We have to measure if it's faster. But for me, I like to write Dart stuff.
Anybody else? Any more questions? No. Right, amazing talk.
Thank you.
All right, and also Tom for helping me put this together. Tom from Few and Far, please speak to him.